their previous record was something like 12. And the reason? Shell brought 29 people in. Exxon brought close to that number of people in. All these companies were coming in because it was the first time that somebody was talking about what was going on in the play. If we had questions, the presentation took 5 hours. Well, I was right further on land, I was right further on geology, I was the one that said to the engineers, don't frack this like we're fracking sand wells like we were doing before. We have to frack it like the Haynesville-Bossier. We want to frack it at high rates because we want to rubbleize rock, you know. And so basically I did the entire 5-hour presentation. So I basically just came and lived in Tudor Pickering's office to do that. So it was very interesting. So then we turned around, there's very little land to pick up. We was able to make deals for 5,000 more acres. We drilled a couple wells on that 5,000 acres. And then we sold that to Rosetta at the same time that Comstock sold their 5,000 acres. We sold her for $85 million. So now I turned around and said, okay, I went from 45 down to 5. I can't put anything else together. Okay, I can't get anybody interested in it. So what do I do? Okay, and so this is the answer to this. Or here was my thought process, and my thought process was, okay, I can't go compete in the Midland because everybody from Midland I had already seen that the Midland Basin had already come into the Delaware Basin. And now I'm not competing with small independents, and I can't buy acreage at $50 to $500 an acre anymore. I'm going to have to pay $30,000 to $50,000 an acre. I can't do that. I can't get financing to do that. So what am I going to do? I said, look at all these great source rocks we have. We were just talking about this. All the great source rocks we have in all these basins and all these plays. And I've got a lot of data in the Midland Basin already, Permian Basin. I want to stay there. I started looking around. I said, Woodford. I started looking into Woodford. The Woodford has sourced more of the traditional reservoirs than any of the other source rocks in the Permian Basin. I said, oh my goodness, it's got to be bigger than the Permian section, the Wolfcampian section, as far as the source rock, and it is. People have played it for years. And what they drew is they drilled Devonian wells, and they would drill Devonian wells, and they'd strike out on the traditional play, and they go, yeah, but we had a show in the Wolfcamp, so let's perforate it. And they perforate it, and so the Wolfcamp quickly got known as all show, no dough. It wouldn't stay. And it wouldn't stay primarily because of the clays, and we're going to look at that picture. So I said, okay, there's 10 things I look at for a resource rock, when I look at resource rocks. 10 things I look for. Mineral composition, TOC, brittleness of the reservoir, and clay. As Bill's already pointed out, clay. And I said, the only negative about the Woodford is the clay. This is 2012. And so I started doing research and working on, and I put some prospects together, which I'm going to show you, on the Woodford. And this was about 2.5 years before the Alpine High announcement was made. And I started presenting at APG. And I called it the stealth exploration for the Woodford in the Permian Basin, because the only other Woodford that was being done in Texas is up along Sherman in the Ardmore Basin, which is a continuation of the Oklahoma place. So when we go to APG conferences, there were 90 guys talking about the Woodford in Oklahoma, and there's one guy talking about the Woodford in Texas. 6 months before the Alpine High announcement came out, RS Energy out of Calgary, a research center firm, put out a paper called Apache's Stealth Exploration Play in the Permian Basin. So when people in New York and in Houston, they cross-referenced stealth, and they found my paper. So it turned out for 6 months of great consulting work, okay? Because everybody said, well, what do you know about the Woodford? You know, they call me up, well, what do you know about the Woodford? I tell them a little bit about the Woodford. And they get to that point where they finally asked enough questions. I'd say, well, yeah, you know, I've got this, and I can come teach a half-day class for you. And so it turned into great consulting. So sometimes just being in the right place at the right time turns into the consulting work, and that's what happened here. So look, I'm going to go through these kind of quickly and just give you some general information. There are a number of slides that are going to be repeats because I don't always do these talks together. We just talked about this. There's 6 Phanerozoic time intervals that account for 93% of the source rock for all the hydrocarbons that have ever been produced. And as we play those source rocks now, that number is going to go up. It represents 33% of all Phanerozoic time, but it accounts for less than 5% of the sedimentary record. So if you're looking at that 5% versus spending your time on the other 95%, you're already way ahead of everybody else. So what you want to look at now is, I'm not going to read all these points. Look for the stuff in white, because that's what's changed, okay? So I just gave these numbers, 25%, and I got these numbers from Marlon Downing and from Fred Meisner, and great practical geologists that understood enough geochemistry, and Fred actually is a very good practical geochemist, and he passed away a couple of years ago. But when I started working with Marlon Downey, he said, you got to go talk to Fred Meisner up in Denver. I'd go up, I had a regional office in Denver, so I'd go up there and I'd visit the guys at the regional office every 2 to 3 weeks, and I'd spend 2 days with them. And then I'd go spend a day and a half with Fred Meisner. Fred, just talk. Just keep talking. I learned so much from him. But so we went over these numbers before. 25, and these numbers I actually learned at Marathon in the early 1980s. 25% of all hydrocarbons from source rocks are expelled. 25% of that is trapped, and then we recover 20 or 40% of that. That's the number I forgot to put in that equation. So 75% in source rocks, and I get a 5% recovery factor, I'm going to recover 3 times as much oil that's been produced in the traditional reservoirs. I took those percentages, and I took the smack over C, this is in the 1980s, when we started looking at onshore salt dome traps. And I was concerned about the fetch area. And so I looked at every field and all the drainage areas and all the Mesozoic salt basins. And I made a simple XY plot. What I predict of how much oil ought to produce, how much oil it actually produced. I used these ratios. And I used the smack over C section as my source rock with 2% TOC, 600 barrels of oil per acre foot, with 1% TOC, multiply that all together, did the fetch area, said here's how much that field ought to produce. It was almost a perfect correlation. Every field onshore Gulf of Mexico, and use those percentages.
Just touch the mouse on the screen. I think it'll go back to the full screen.
Something died, Linda.
Something died. If you just touch the screen with the mouse, there it goes.
All right. So there's our rock section. So let's look at those 6 time periods. There's the Silurian, and I'm going to go through these fast. I'm looking at the period, the percent of worldwide, some of the North American examples, and some of the international examples. And so you'll see, when you measure these out, North America's got great. So there's the Silurian, that sourced a lot of the Permian Basin. There's the Devonian through the Carboniferous, which is mostly the Woodford. We looked at the Wolfcampian, or Penn section there, Wolfcampian. Here are the ones in Gulf of Mexico. We talked about the smack over C, the Kimmeridgian, which is the same source rock that we've got in the North Sea, the Mid-Cretaceous, the Oligocene Miocene. Those are your 6 periods that account for all that oil. So what we want to focus on in the Permian Basin is, look at the North American examples, that lower Devonian section, the Bakken, the Woodford, the Marcellus, and now the Marcellus is a little bit slightly different age, and Niobrara, and I didn't even put the Woodford on there, did I? Yeah, the Woodford's on there. All right, so I did this work actually in graduate school, but then I redid it at Marathon, and when I started at Marathon, I started the week of budget. So somebody showed me how to color yellow, and on which side of the SP line to put it, and we had probably 20 geologists and 5 geophysicists and 10 linemen in that division. So I ended up with 0% of the budget for the next year. When the budget rolled around the next year, I had 85% of the budget. It's because I started with the tectonics, I did the tectonics to basin evolution, I did the basin evolution, I came up with 3 new plays. In 1982, I had 300,000 acres in the Fayetteville Shale play. We owned that play. But at that time, I thought the Fayetteville was sourcing the Ordovician traditional reservoirs. Just a little bit ahead of the play. But I did this work. So here's the rifting that occurred, and you can see down at the bottom in red there, during the Precambrian and the Cambrian, we had rifting. And the point on the rifting is we had a series of triple junctions. Here's a triple junction, arm, triple junction, arm. What happens, two of those arms continue to rift. One of them becomes a failed rift, which becomes an allocogen. You see one goes up through the southern Oklahoma basins. I have one coming up through the Permian Basin, and then we broke right along the Appalachian. You can see the real foot allocogen, and the real foot allocogen is the only one that's not a big source rock. So it broke along that red line, and North America broke away from Africa and Europe. So there are those failed rift arms as we go up into the Devonian and lower Carboniferous. So those started as rifting and rift shoulders. As rifting continued, they became normal faults. We had depressed areas, and we formed big basins. And we formed big basins, and you can see the real foot allocogen, the southern Oklahoma basins, and the Permian Basin. And that's where the Woodford was deposited during that period of time. And that just takes it up into the early Mississippian time as we drowned out those sources and go up into the Mississippian. The Mississippian line, the only time I have time to mention this, so after we made those plays, the owner said, don't we want to go play the Mississippian line because it was hot at the time? I said, no. It's not a resource rock. It's a migration pathway, much different type play. I'd worked that since I was in graduate school at Missouri because that's where those rocks crop out, so I knew that's what the play was. So that's where we were in the late Mississippian line play, but here are all the late Devonian resource basins. All the major basins in the United States have something that's either Devonian or lower Carboniferous, Mississippian age. So these are the intercrontonic basins, the Michigan Basin, the Illinois Basin, and the Wilson Basin. And those are the failed allocogens, which were the Anadarko, Oklahoma Basin, and the Permian Basin. And then as Bill showed, what happened in the lower part of the Carboniferous as North America and Europe and Africa collided together again, that collision started up in Canada. It zippers its way, is the way I phrase it, down into here. And as it was marching along and doing that, as the collision starts, you start loading crust on crust, and you start with a big depression. That's what starts those four-line basins dropping down. So the first thing that happens is those basins drop down dramatically, and you end up with source rocks, because you have a deep basin marine setting, and you end up with those source rocks. So it started up in the Utica and Marcellus up in the Appalachian Basin, and as Bill showed, it zippered right around into the Black Warrior Basin is now called, into the Arkoma Basin, into southern Oklahoma. Now southern Oklahoma didn't develop as a four-line basin because as this happened, the four-line basins, if this is perpendicular movement, you form a four-line basin, but you can see the movement this direction was parallel to those major faults, so you started major strike-slip faults through that area. So what happened in the Permian Basin? Was it a four-line basin or a strike-slip fault basin? Yeah. So those are those failed allocogens just with a blow-up of what they're doing. And look at the diagram that I've got for the Permian Basin. If you look at the Permian Basin field studies that have been done for 80 years, and you go look at individual fields, all these faults are mapped as reverse faults. They've got thousands to tens of thousands of feet of vertical displacement. So if you're looking at a postage stamp and you're looking at it makes sense to map that as they're not. They're strike-slip faults. Tens of thousands of feet of vertical displacement, miles of lateral displacement. So that's what was happening in the Penn section, and actually after that collision happened, the Permian continued to subside, and actually in the Gulf Coast, underneath the Triassic sediments, there's Pennsylvania section sediments. And so that was one of the plays that we developed in the 80s as we looked. You guys know about the Jurassic section. We don't have, so those are all the major resource plays by basin type, and that is sorted by geologic period, and that one is sorted by basin types. So Charles, there's a diagram for your major paper that you're working on. That's the distribution of Devonian black shales in the United States. So that's very difficult for other countries to compete with that distribution of basin and plays. So we already talked about why do I want to concentrate on those condensed sections. Stratigraphy, understanding stratigraphy, and understanding sequence stratigraphy is critical to making some of these resource plays work. We've already looked at these diagrams. So I want to identify that maximum flooding surface, and that's what I'm going to look for the high organic facies immediately above and below, and including that facies. And guys, I'm saving time here, but you've seen those diagrams before. I'm also looking for high percentages of brittle framework grain composition, and Bill's already talked about this. If I do a triangular plot of most of the Paleozoic compositions, I end up with a lot of brittle framework grains. Let's look at Mesozoic basins. What happens? A lot of clay in a lot of the Mesozoic basins. So it's not only true for the Warrior Basin, a lot of the resource rocks that are in the Gulf Coast, great source rocks. There's the Wilcox source rocks, great source rocks. The Tuscaloosa Marine Shale, great source rocks. What's their problem? Too much clay. Too much sediment from outside the basin was coming in at those various times. So there's the sweet spot. Compositionally, I want to be between silica and carbonate, and I want to be in that clay facies, and every once in a while I want to mix in a little silts for a little bit better porosity and permeability, and that's the sweet spot as far as that's concerned. I want slow sedimentation rates. Again, that's what's wrong with the Cretaceous basins and trailing margins. They had really high sedimentation rates as opposed to what we saw in the Paleozoic period. So that, I was just showing some of the debris flows again, and the difference between slow sedimentation above that red line, which is top of Sheldon, and very rapid sedimentation when we get in those carbonate facies, and look at the amount of organic material in the carbonate, which is very fast sedimentation, versus the organic material that I've got in the very slow sedimentation. As a matter of fact, the only spikes I have are breaks in the debris flows. So debris flow, break, a lot of organic material. I went back to the basinal sedimentation to do that. And I want well-sealed, brittle source rocks developed in an organic fracture network system that enhances hydrocarbon recoveries, and I want non-tectonic fracture systems. Why? Tectonic fracture systems don't just break up the source rock. They break up everything. And when you break up everything, you're either going to bring in water from below, or you're leaking off all your oil in those kind of systems. And so we looked at some, these are well-sealed source rocks, and I've gone through that history of I know they're well-sealed. So when you go to that red line, which is a slope boundary, two things happen. The dip increases, which leads to additional leakage, and I get in sandier facies, which allows, when the pressure develops, it allows the pressure to go up slope. And so that's another reason that the basin center are so well developed, and when you get up on the slope, you don't have pressured systems because the pressure leaked off when it got up into there. And the reason I didn't want to be on the eastern side of the Delaware Basin is there's a lot more faults per mile than there is on the gentle slope. So that also is breaking up my seal structures. As a matter of fact, Pioneer and a couple others had studies that they've reported on that when you drill wells near faults, even if there's no displacement that you can observe, which means there's no vertical displacement, there may be lateral displacement, there are seal leaks, and the recoveries are lower when you get near those types. So North America, we've had an accretive history as opposed to some continents that have mostly just been collisional histories. In that accretive history, even though we have multi-basin phases in North America, they're generally one very active phase, and then the other phases are very inactive phases. So if we look at the lower 48, Devonian, that's that big circle, and then we've got a lot of other basins that are represented there. So we end up with large, structurally non-complex, undisturbed basin centers with deep flanks that result in excellent preservation of hydrocarbon and source rocks and easily defined targets over large areas. And that's why we have so many good source rocks in North America, as we've already looked at in the Delaware. All right, so now I'm going to get to the Woodford. That's an isopack map of the Woodford. So I started saying, okay, let me make some basic maps on the Woodford and understand why that play hasn't worked and where it's going to work. And what's interesting about that covers the entire Permian Basin. Where's the Central Basin platform? Where's the Midland Basin? There wasn't one. There's one large basin called the Tobosa Basin. This is on top of that failed location that we looked at before. Those purple colors are about 600 feet, and this entire area that covers the Midland Basin is about 100 feet in thickness, 600 feet, and then here's where the Alpine High. What part two that we're passing by is, I started taking a bunch of those maps and saying, okay, there's a bunch of extensional areas, and when you have a bend in a wrench fault system, and that bend is transpressional, you get a pop-up high. And guess what? I started looking at every major field that was on the Central Basin platform and in the basins, and I said, oh my goodness, they look like exactly where I'd predict them to be with pop-up highs. And so then I started saying, well, I don't want to map the highs, I want to map the lows. So I looked at transtensional areas. And I found some transtensional areas, and when I found those areas, I found a lot more sediment thickness and a lot more sediment. There's even a lot of missing section, and I found some of that on the Central Basin platform. And so I put together a couple plays off of those maps. And that's what those are, and actually we made some Woodford discoveries prior to the Alpine High, but guess what? It was stealth exploration at the time. We weren't out publishing those things, but I put together a series of those plays. This is information from Apache about a year before they announced the Alpine High. Actually, this was about 18 months before they announced the Alpine High. And this was from their report, and they're talking about all the different potential future targets as well as their current targets that they're playing. And when they drilled in the Midland Basin, look what they came up with. So I talked to an independent here in Houston that had a very small interest in some of those Apache wells. I said, what's that all about? And what we were doing at the time, and remember this is the same time frame that a little bit after we were drilling those vertical wells in the Delaware Basin. They were drilling vertical wells, and they were completing them with 12 stages. And they were completing 10 or 11 of those in the Sprayberry Wolfcamp section. And they drill all the way down to past the Devonian. And they had shows of oil, so they put one in the Wolfcamp. And they started producing. I said, what was your initial production? They did spinner surveys and identified where it was. They did tracers to identify where it was. So they had 12 stages. So if you get equal production out of 12 stages, is that 8.5% ought to come from each stage, right? 40% of it was coming from the one stage they put in the Woodford. So I thought that's pretty interesting. And that didn't happen just once. Look at all that. It happened time after time after time. Now, a couple months later, the same thing was happening. They come back. The Woodford was hardly producing anything. But it told me it's got potential, right, to be able to produce. So Whiting had a paper. They did the Woodford up on the Central Basin platform, which was right here. And one of the plays I had put together is right there. And so this was a very interesting paper that they did. There were a couple people that had completed in the Woodford, and you can correlate not only zone for zone, you can correlate bed from bed from the Permian Basin to Grady County, Oklahoma. Exactly the same sediments at exactly the same time, and they correlate. So these are all the zones. This is the interval that they perforated. There's the mud log. As I said, if I only have one log, that's what I want. It tells me I've got the oil in place there. There's the structure map on top of it. I'm going to point out a couple of things. Look at the TOCs they had. Really great TOCs. Look at the R sub O's that they had, and they were producing that at about 8,000 feet. So, but their conclusions were 0.7 is too high. Fracture work. Someone asked about the fracture. Fracture network alone is not enough for the storage. 41 API. Guess what? It's 37 to 38. It's not 41. When you look at the Permian Basin, you're going to see everybody on Permian Basin reports their oil. They all put in 41 or 42 degrees. It's all pencil whipped. It's not measured. It's not careful. Everybody puts in 42 degrees. So you have to be very careful. You have to actually get the data. That's the only thing I went to the University of Missouri for was so I could learn to say to everybody, show me the data, right? And show me the data. So when I looked at the data, I found out it wasn't 41, it was 38. There's the production and data information. So I said, okay, 37 gravity oil in that tight of a rock. Is that a big difference? Well, if I look at the viscosities at the surface, if I look at, and I come up to 42 gravity oil, and I look at 37 gravity oil, you just say, well, that's only 4 or 5 degrees API. Is that a big difference? At the surface, you have twice the viscosity with 37 gravity oil than you have 42. I said, oh my goodness, when I'm dealing with you remember back when the Barnett was the only thing that worked? And what did we say? Well, I don't understand how this works because a methane molecule is this big and it's bigger than those pore throats, so I don't know how it's working, but George, great job. Glad you're producing, but this will never work for oils, right? And so when I started looking at these kind of viscosity numbers, I said, that's a problem. Now, I don't have it diagrammed here, but if I actually take 37 gravity oil at 8,000 feet and I compare that to 42 gravity oil at 11,000 feet, the difference in viscosity isn't half or twice, however you look at it. It's 1/3 to 3 times. Oh, okay, that's another good indication of what I want to do. So I said, okay, there's my isopac map. And this was actually done by Ken Bailey at Hunt Oil. He was actually looking, and when he was mapping the clay faces, he was actually doing the framework grain compositions, and he came up with an amazing, it's hard to see, this one all plots in the dolomite, there's a bunch of pink right here in the pink, this one's all pointed out as quartz, and this one's all pointed out as clay. And I said, well, Ken, how many wells have you done that for? He goes, oh, I've only done 24, but they're randomly distributed around the Permian Basin. So I took his data, I didn't plot where the data was, and I started making cartoons in the Woodford. And now look at the Midland Basin. It's covered by kind of shaly dolomite where they got 40% of their oil production in their early wells. Look at the Delaware Basin. And I took a different cartoon. Multiple working hypotheses, right? And I still came up with multiple ideas of why I should get there. So here was a master's thesis, and this guy went through the 10 things that I want to look at for an organic sediment. Okay, there he's looking at TOC, that's looking pretty good. Vitrinite reflectance, 0.5 to 2.2, that's looking pretty good. Shale thickness, good. Gas-filled porosity. Clay content, no, that's a little weak. Quartz content, good. Fluid compatibility, not so good. That's because of the clays. Natural fracture, yep, got that. Tectonic stress, got that. Pressure, looks good. I put that on the chart. Actually, this is his work. And if I look at that, the only places that rank, and I'm ranking this 1 through 10, is clay content. That's not a very good number. And fluid compatibility. That's not a good number. What's fluid compatibility? Clay. Said, okay. I now know the one thing I need to work on. When I do rows statistics on traditional plays, what I found out from experience is if I multiply the things together and I come up with a certain probability, if that probability is low because of one factor, I probably am predicting pretty well. But if that probability is a result of 2 factors, I'm done. Okay? I want to get it down to 1 factor. So now I'm looking at 10 factors instead of 5 like I do in rows. I've got it down to 1 factor. So if I can control that 1 factor, I got to play. And so here we talked about the zones which matched what we have in Oklahoma. This again is all the work from, this is from Broadhead, New Mexico, probably that guy's thesis advisor. There's the Woodford thickness. That's in New Mexico. You can see Texas on the south side and the east side there. There's the Woodford thickness interval. There's the TOCs increasing as I go towards Texas and the southern Delaware Basin. And there's the productivity index. The productivity index, he's looking at mobile oil versus how much oil's in place. And he made these nice maps out of it. Well, I took his data and I said, oh, by the way, here's his 3D diagram. I'm thinking in those lows also. Well, here's Parsley Energy, and Parsley Energy was mostly a Midland Basin company, and then they came out and they picked up this Trees Ranch acreage right over here. They drilled that Trees Ranch acreage, and they drilled right here, and M.L. Hansen, do you remember M.L. Hansen? She worked for me. She wanted to get back to Midland, so she went to work for Parsley. So they were drilling a Wolfcampian well. And I had started my Woodford work. So you go, why don't you drill out of the Woodford? They drilled to the Woodford. They did 12 stages, 1 here, 11 here. So again, 1/8 of the production should have been coming out of the Woodford if everything was equal. So I asked one question. I got one question. So I said, what percent was coming out of the Woodford? Guess what her answer was? 40%. Great answer. That's all I needed to know. That's all I needed to know. There's the design of the well. I guess they put some in the mist and the Penn as they were doing some of their work over here. So here's interesting. Here's the Waha. There's a big facility there. That's a big field. This is a low, just kind of like those transtensional lows that I showed you on the Central Basin platform. This one actually is out in the Delaware Basin. Here's the Trees Ranch acreage through there, and I couldn't get any of the parsley wells. He's going to go back. But look at there's where Parsley drilled 3 wells. By the time they drilled 3 wells, I said, look, let me go get that A.G. Hill Trees No. 1 estate, drilled down to 17,000 feet. Oh, I should have put the year on there. Drilled a long time ago. But I couldn't get Parsley's wells. So I got the Trees Ranch wells, and we ran a new tech log on that, and look at the free oil in that middle column in black through the Woodford. And again, I could correlate that Woodford to northern Delaware Basin, and I could correlate it to Oklahoma. And so again, I said, okay, we're in the right facies. And then I looked at the Woodford in those transtensional basins that were formed on the Central Basin platform, and there's the new tech logs for that. The Trees Ranch well is on the left there. So there are 3. So that's Apache's presentation about 3 to 6 months before the announcement of Alpine High. And this is their acreage position shown in yellow. Bad diagram, I know, but here's where they have 300,000 acres. Look how much they're reporting that they had in the Alpine High at the time. And here's just a quick 2-well cross-section across there, just showing that you can say all these lower Woodford facies. Once you get up on the Alpine High, there's faulting, and you're on the margins of the basin. I agree with Bill, it's part of the Delaware Basin, but there's some irregularities that you need to know about. That's the thickness differences coming across some of those faults. And so this section, which drops down to here, you've added all this section on the downthrown side of those faults. That's Barnett, that's Penn Shales, and a thick can come up with some plays, I guarantee it. Because I've done it. I've done 2 or 3 plays like that. Here's some of the highlights from the Alpine High area of what they've shown. Bill's shown some of these diagrams. That should look familiar. There's the downdrop section. A lot of these are simplified. I hope as geologists you have problems with some of these finance displays. Don't show everything that we need to do. Comparison of what they're doing and looking at. And as Bill said, part of the story is you go from the Midland Basin, where we have 50% clay in the Woodford. As we come into the thick in the Delaware Basin, there's much less clay. So there's more plays out there than just the Alpine High as part of that story. Okay.